you don't need to know it for this example. So the main thing is, cosine satisfies this, sine satisfies this. Okay? So this means we can simplify this one into sine of alpha. Let's drop the parentheses. Because cosine negative beta is cosine beta, we just say sine alpha cosine beta. It's the same thing. And then because sine of negative beta is negative sine beta, we can just, the whole thing becomes negative, so it becomes negative cosine alpha sine beta. Right? And now what we can actually do is if this was equation 1, and this was equation 2, so here was sine of alpha minus beta, right? If we took 1 and then we added 2, we would get double this, but these two would actually cancel out, and we would get these two things added on this side. So you get sine of alpha plus beta plus sine of alpha minus beta is going to be, so just adding these two sides together, this one and this one together, I'm just writing it out. And adding these two, they're the same thing, so it becomes 2 times sine alpha cosine beta. And then this is plus cosine alpha sine beta, this one's minus cosine alpha sine beta, so they cancel out, and it becomes 0. So we get this. And, yep. And this actually helps us already simplify it, because look, what did we originally have? We had sine of one thing, A, plus, okay, let's not do that, just to avoid confusion. Let's say sine of, something x, right, plus sine of y, which is a different thing, right? Well, we can actually use this formula to simplify this. Because what if we just say, let x be alpha plus beta, so x equals alpha plus beta, and then let y equal alpha minus beta. And now we can solve for alpha and beta in terms of x and y. So we add these two things together and it becomes x plus y is equal to 2 alpha. So add these things together, you'll get that because betas cancel. If you subtract these two things, then x minus y is going to be 2 beta, because alpha minus alpha is 0, but beta minus negative alpha is 2 beta. So, adding these two equations gives this, and subtracting these gives that. And so that means that we can substitute in alpha equals x plus y over 2, and for here we can substitute in beta equals x minus y divided by 2. And this gets substituted into there, right? So because if you substitute this here, alpha and beta, you can even try it. Just substitute these in algebraically, simplify. You'll get x here, and you will get y there. And so what does this all mean? Well, at the end, what we've gotten is an equation that tells us that sine of x plus the sine of y is going to be 2 times the sine of alpha, but alpha was x plus y over 2, so it's going to be x plus y over 2, and beta is going to be x minus y, cosine of x minus y divided by 2. Okay, so that's very interesting. Well, now that we have this, let's look at the original thing again. It was sine of omega 1t plus sine of omega 2t, right? 2 different frequencies added together, interfering. How do they look like? Well, just plug in omega 1t for x, omega 2t for y, and this whole thing is sine of, again, if you simplify, for the sake of time, I don't really want to skip too many steps, but if you just simplify, plug in this one for x and plug in this one for y, and you simplify this, then you will get that x plus y over 2 is the same thing as omega 1 plus omega 2 times t. And then here, this is going to be cosine of omega 1 minus omega 2 over 2 times t. So, what does this say for us? Remember, this is a frequency, right? So this is actually now some kind of a new frequency, and then it's multiplied by something. So you think, well, originally we had 2 trig functions added together, but now we have 2 trig functions multiplied together. That must be even more complex, right? Well, actually, no. Multiplying trig functions actually is much easier than adding them, or graphing multiply trig functions is much easier than graphing addition. Why is that? Because trig functions have this thing called an envelope, which means that if you have, like x squared times the sine of x. So if you remember from algebra, x squared is a parabola, so it looks like this. So this means that sine of x is going to be multiplied by this. So what happens is if you graph it, then it will actually look like this with a reflected parabola. And then the actual graph is going to have sine of x look like this. And then it's going to come here, and it's going to... So it's actually like, it's kind of like a sandwich. And then the wave actually gets sandwiched between this wave, and then it increases this way. So, so if this, if this sine was actually very high frequency, so let's look at another graph. So you might have some kind of a line, so x times sine of 100x, so a very fast frequency. So x is just, the 45-degree line here, and then it reflected is going to look like this. And so you're going to have sine of a very high frequency. It's going to look like, the graph of it is going to look like this, inside the line. Yeah, you can try it on a graphing calculator, and it will do this. So the whole point is that there's something, the thing that gets multiplied by the higher frequency trig function is going to be called the envelope. And the trig function itself is the carrier of the thing. This terminology actually comes from radio. So a long time ago, well actually no, they're still using it now, but they had this thing called amplitude modulation, or AM radio, which actually has a very fast frequency. So you have music, that's playing, maybe here this is the wave for your music. But the whole thing is if you actually transmitted this through the air, it would actually be too low of a frequency, and then it would in the air it would just slowly dissipate. So nobody would actually be able to receive this because there's so much noise and everything, it would just get rid of this signal. So what they discovered is, well, you can actually carry this big signal inside a much higher frequency signal. And so the higher frequency signal kind of gives this shape as an outline, but it itself doesn't actually use this frequency. And so then this thing then becomes, the envelope of the thing, and then this higher frequency becomes the carrier wave. And this is how amplitude modulation radio works, is you sort of have a very large curve, and then you have a very high frequency curve inside. And also for the stock market too. If you look at it, it sort of fluctuates a lot. But if you just draw the whole trend over the day, you can sort of see it has some kind of envelope around it. So this is the concept of an envelope and carrier. And here in this trig formula, we also have an envelope and a carrier. So let me just give a concrete example of these two things. So let's say I had sine of 10t plus the sine of 11t. Okay, so this is the whole thing. It's like, well, these two frequencies are actually really close, but they're different. And then, as you can see, the interference from notes actually gets worse as they get closer together, right? So let's see what that is. So if we just use this formula, omega 1 was 10, omega 2 was 11, and we plug it in, it becomes 2 times sine of 10 plus, I'm lazy, so I don't like to have fractions, so let's change this to 12. So it becomes 10 plus 12 divided by 2, which becomes 11t. And then we get cosine, and then 10 minus 12 over 2, which is going to give us negative 2t. But remember, cosine of negative 2t is going to be the same thing as cosine of 2t, because cosine is an even function. So we get this. So that means this is a much lower frequency function being carried by this high frequency function. So how is this actually going to look like? Well, it's actually going to look like, this is going to be, it's a cosine curve, so it looks like this. And it has a very low frequency. But inside, it's actually, sorry, these graphs are horrible and asymmetric. But yeah, so inside, this is actually going to carry a very high frequency sine wave. And so, so the first thing is, we sort of reflect it, get the whole envelope. And then inside, then we can draw the high frequency sine wave like this. So it's not to scale, I'm just giving an idea. And so you see this thing is wrapped around and it kind of goes up and down, up and down, up and down. And this is exactly the notion of beats that we heard when the piano was playing, and then you actually hear this interference between the notes. Because if you think about it, the closer these actually get together, the longer the beats are actually going to be, so the more noticeable these beats are actually become. And so this is how beats actually originate in music, using all the stuff in Trig that we have learned so far to explain this phenomenon. And also, in the meantime, I know I covered through a lot of things, and I don't really expect everything to be digested right away, and probably just rewatching this video isn't enough. You probably have to look at other sources. But I hope that this whole presentation of all these things motivates why trig is so important and how it can just apply to subtle things that doesn't seem to have anything to relate it to right triangles from the beginning. So if you recall, just all the way in the beginning, we started with right triangles, then we went to sine and cosines. We started to do things like the sine sum identities, cosine sum identities, which we discussed, right? We have the Pythagorean theorem that helped do a lot of things. And then we talked about the unit circle and how it generates waves. And then, we applied all those concepts together, and it, it created this very nice framework allowing us to actually model this real world physics type of problem with acoustics and interference and where beats come from. So I hope you at least find that interesting and motivates to go and study the topic some more and look at it in more depth. Depth is very important.